Good morning. This is Tim Stewart. I am president at Visual Decisions, and we are here today to talk about improving quality in manufacturing with the combination of operational excellence or lean manufacturing and Industry 4.0. At Visual Decisions, we've been in the business of utilizing information from the shop floor to improve continuous improvement since about 2002. We help our customers combine the smart factory with the lean factory to drive improvements to cost, throughput, and quality. Our customers have seen dramatic improvements such as 30% increases in OEE, 50% scrap reductions, and much more. But just like wearing a Fitbit won't automatically make you thin, implementing technology for Industry 4.0 won't automatically make the business better. The culture of the organization and the business processes have to be adapted to take advantage of the new capabilities to drive real improvements. That's why we have a unique approach to work with our customers to adapt processes to take advantage of the new capabilities and help establish a true data-driven manufacturing culture. So why add Industry 4.0 solutions to lean practices? This is a graphic from Bain that came out in 2019 that just shows how much of an improvement you can get in the purple with lean manufacturing alone, and significant improvements across the board for output, for quality, for inventory reduction, et cetera. And then if you add on digital capabilities on top of that, then all of those different improvements can actually be significantly higher. And so there's definitely reason to add in those digital capabilities on top of lean. But for a lot of companies, manufacturing has embraced technology and automation, but continuous improvement has not. And so when you look around a factory floor, you can see robots and cobots and augmented reality and laser welding and all kinds of fun things that 15, 20 years ago seemed really futuristic. But then you see the continuous improvement boards, and they're still done on whiteboards, or you're printing off stuff and taping it up, and it is just not hasn't embraced technology the same way that manufacturing as a whole has. And so if we look at how to transform operational excellence to take advantage of those new capabilities, there's a couple of different categories that I look at. One is a lean management system, and being able to bring that those digital capabilities into the lean management system, whether that's the management operating system itself, visual controls, how you do standard work, daily accountability processes, how do you make Gemba more effective, et cetera. But then there's also the toolkit side of things, how you actually perform a root cause analysis, how do you do value stream mapping or an FMEA, and much, much more. And so those are some of the things that we'll cover today. If we look at just a basic Kaizen process, and this is actually going back in time, what drove me to combine the digital technologies with the lean practices, because I was working at a lean manufacturing consulting company, and I got frustrated working with customers that had no data. We would go in there and they'd want us to run an improvement event for them. And we asked, okay, well, how did you pick this particular improvement event? And they would say something like, well, this machine went down last week, and so we need to do a Kaizen to make sure it doesn't go down. Or well, we have a lot of problems, but Joe talks about this one all the time, so we're going to do an improvement event to basically shut Joe up. And it was usually either the machine that went down last, or the person that was shouting the loudest that would get the improvement event in their area. And then we would go to run the improvement event, and we would be out there with a clipboard and a stopwatch for 2 weeks, 3 weeks, however long it took to gather enough data to do a proper root cause analysis. And it seemed to me like there must be a better way. And it felt like the lean tools themselves needed to be much more lean by having the data already present. And so if we look at a typical 6-step process for Kaizen, where we identify the problems, analyze the current processes, create solutions, test those solutions, measure and analyze the results, and then standardize, every single one of those different steps can benefit from additional data being available when you take that step. Certainly, if you're looking to identify the problems, instead of just working on the machine that went down last week, if you can identify what are the actual biggest opportunities within the plant from a throughput perspective, cost perspective, or any other significant metric, then you can make sure that you are pulling on the biggest lever to improve the operations for the facility. If you look to analyze the current process, certainly, their data is going to be very helpful. As you do root cause analysis, you're going to want that information about what is driving, the current problems and so forth. And then creating the solutions, testing the solutions, measuring and analyzing the results, et cetera, all benefit from those additional data capabilities. Taking a deeper dive into root cause analysis and many different frameworks for doing root cause analysis, whether you're looking at something as simple as just who, what, when, where, why, how, or 5 whys and asking why multiple times, or putting things into a fishbone or a Ishikawa diagram, graphical evaluation, FMEA. Or if you're going more of a Six Sigma route with ANOVA and design of experiments and so forth, every single one of those benefits from having that data on hand. Even something as simple as the who, what, when, where, why, how, being able to have the data that says, well, when Joe runs the process versus Bob, who runs it better? Do we see the same behavior, or do we see different behaviors? Do we see the same behavior on a Friday that we do on a Monday? Do we see the same behavior when it's humid versus when it's dry? Those are all things that if you have properly contextualized and gathered data, you'll be able to see those trends. If you are out there for 2 weeks with a clipboard and a stopwatch, you're first of all gathering bias data, but you're also looking at data over a relatively small sample time. And if it's humidity that's driving that process and you have a couple of dry weeks in a row, you'll never actually be able to see that in order to make that correlation. And so, there are a variety of different things that for root cause analysis, you just need that extra data, and having that extra data is going to be extremely beneficial to that process. Something as basic as standard work, being able to incorporate these digital tools into that can significantly help with standard work. And whether you're looking at creating the standard work in the first place, or the adoption of the standard work and the utilization of that standard work, out on the shop floor, the digital tools can help with all of that. Obviously, with the authoring, that can make things a lot easier. There are, augmented reality expert capture systems these days that allow you to have your experts in a process, where the glass is, whether it's a Microsoft HoloLens or a RealWear, any of those different options, and basically just take snapshots or movies as they're doing their work, and then create the annotations that can dictate them, as they're doing the work. And you'll see that step-by-step process for how things are actually done. And by the way, if you're doing a SMED analysis, they can wear those glasses as well. And you can get through every single step in the SMED in that same way. But now if you're looking at how you actually get standard work out to the field, how do you communicate that standard work? Again, those augmented reality solutions can help immensely with that, from a training perspective, as well as from a day-to-day ongoing perspective. Being able to put screens out there that give people that real-time feedback and so forth, but then also having the data being captured to be able to see where are people not adhering to the standard work. How do you detect and elevate attention to the deviations from those standards? And so there's a tremendous interaction between standard work and a lot of these digital technologies. Something as old school as a FMEA, or a failure mode and effect analysis. has huge opportunities to benefit from that digital conversion. So I grew up doing FMEAs, where we locked ourselves in a room for 3 straight days, or however long it took, and we would start brainstorming different failure modes, different effects of the failures, and so forth, different causes, potential causes for those different failures, and so forth. And we would just have that cross-functional team locked in that room for 3 days, 5 days, however long it took us to get through the process. And then we would basically stick our fingers up into the wind to be able to guess how severe was the issue, what was the probability of occurrence, what was the probability of detection, and from that being able to get our RPN. And if we look at how you can digitize this process, if you have something like an OEE system out on the shop floor where you're monitoring the equipment and pulling in information about the different downtimes and so forth, or quality issues, essentially you're collecting all of this information. How often that machine is going down. You are capturing the reasons why it's going down and so forth. If you already have an existing FMEA, you can utilize the failure modes from the FMEA as the different reasons that you're capturing within the OEE system. And now you can actually calculate from the data, what is the probability of occurrence? How frequently does that occur? When it goes down, how long does it stay down for? And so I can, have that as an input into the severity measurement and so forth. The probability of detection will be 100% if I am, actually seeing that failure and being able to capture that failure and so forth. But we can think of that probability of detection as something where you can utilize that to guide what variables you're capturing from the machines. And so if I have different failure modes that have a low probability of detection now, how can I utilize these technologies in order to automatically capture when that is occurring and when it's not? And so I can start to implement, machine intelligence and so forth to infer when different things are happening based on the combination of several different process variables, whether it's sound or vibration or power consumption, or any other tag coming from that controller. And so as I gather that information from the shop floor, I can tie that into my different failure modes, my different causes, and then feed that back into the process. And so this can become a closed loop, evergreen FMEA that instead of getting done and going into a drawer or hanging on a wall someplace, it actually becomes part of the daily management process for the operation. Now, one of the concerns that I've heard from traditional lean practitioners is that they're afraid that if they ditch the whiteboards, they'll lose the fingerprints on the data that they currently have. They'll lose the involvement of the people that they have to go up there and write that information on the whiteboard. And for me, that's just an adjustment to the standard work. So instead of having to have people walk, go through the waste of movement to go over to the whiteboard to write that information down, they can actually stay at their machines, have a display right in front of them that has that information mostly captured automatically, but now create the standard work around utilizing that information on a daily basis to improve the process or improve how that operation actually functions. And as long as you can set that standard work and make that part of the culture, you don't lose the fingerprints on the process. You're just adding to the capabilities of the business and having people focus more on the value add part of this as opposed to the grunt work side. So with all of that said, if we look at how we acquire and utilize that information, there is data literally at every single part of the process. This is a little analysis that we did for a bread manufacturer where we looked at, they said that they didn't have information available, but when we actually went into the process, as everything from the inspection, they were maintaining an Excel worksheet with all of their non-conformances and so forth that they saw as they did their sampling at inbound inspection, all the way through the shop floor. Every single process on the shop floor, generated data. They just weren't capturing and utilizing it. And then all the way through the warehouse and shipping, there was data everywhere, but they couldn't see the forest for the trees. And again, there's quality data in so many different systems on the shop floor. And even things that you don't necessarily think of as quality data influence the quality that you're seeing. And so something like information in your maintenance management system can have a big impact on quality, because if you are continually breaking tooling or something along those lines, chances are you're generating bad parts when you do that. And so there's correlations to be made between the information in all these different systems and its impact on your quality performance. One other key is that you don't want to capture just what is happening. If I look at something like first pass yield is captured by most organizations, that make anything. And knowing that my first pass yield went from 98% to 93% is fantastic. But what I really need to know is, why did that change occur? What were the things that happened today that don't normally occur that drove that reduction in my first pass yield? And so that's where we have to get into the diagnostic metrics of capturing, what those failures were, and ideally capturing them at multiple levels so that we can create that drill down, ask why multiple times, to be able to get to an actionable level of information. The next thing I want to talk about is predictive quality, and both what is predictive quality and why is it important. So if we look at what predictive quality is, it's basically having that crystal ball, and it's being able to look at some of the trending, some of the underlying variables for the machine performance and so forth, and be able to predict bad parts before they happen. And to some extent, this is what SPC, statistical process control, is meant to do. It's meant to show you where you are trending, with your output variable, and be able to then say, okay, before we hit something that's outside of 3 sigma, before it's outside of the actual tolerances, we've seen was it 7 points in a row with increasing trend. And so even though we're not outside of the limits yet, we know that the process is no longer under control. We have a drift occurring, and we need to stop the process and make an adjustment. Predictive quality incorporates that type of analysis, but it's even larger than that, where we're looking at, what is the noise from the machine? What is the vibration level? What's the power consumption and so forth? And being able to take that information and infer from it when we think we're going to have a quality problem in the future. Why is this important? The earlier that you can capture a quality problem, the better off you are. I've worked with customers that don't have testing, at that machine itself, and they don't do testing until 4 or 5 processes downstream, and they do things in batches. And so if they wait until they see the signal from the test that they produced a bad part, they may have already produced another 10 entire batches of bad parts before they get that signal. And so if we can, from the data, infer that we're making bad parts just from the signals that we're getting from the machine, rather than testing the actual output variable and so forth, then we can capture that much sooner and reduce the overall cost of rework or scrap. And I stole the thunder from this thread or this slide, but essentially what we're trying to do is to reduce the internal cost of quality, where you both have the cost of poor quality, but also the cost of good quality. If I can get these signals from the machine and infer when I'm making bad parts, then I don't necessarily need to do as much testing downstream with manual labor and so forth. And so I can actually reduce my cost of good quality as well. But certainly I want to, as much as I possibly can, reduce that external cost of quality, because that's where things get really expensive. And so how can I reduce the escapes? Whether that's putting vision systems in place and, more effective testing, but ideally, if I'm able to capture that where it's happening at the machine itself, then I can, make that change up front and reduce the possibility of having those escapes happen. But then I also want to be able to reduce my warranty claims, something that was initially good, but then became bad perhaps. And what I can start to do if I have either serialized parts or lot tracking or something like that, as things show up in warranty, I can start to correlate that with what happened on the manufacturing floor when those parts were made. And now I can start to see, what are the signals that I can see from manufacturing that correlate to things that end up in warranty downstream. That may not be a causal relationship. I have to do further analysis to figure that out. But if I can start to see that correlation, then I can start to see what are the things that I have to control within my manufacturing process to reduce those downstream warranty issues. I don't want to get too deep into a predictive analytics workflow, but initially you have to access and explore the data. You have to pre-process it to reduce the messiness of that data, develop the predictive models, and then integrate that with the data collection process so that you can immediately highlight, alert, et cetera, for when those issues are happening. You also have to be able to contextualize the information very well. And so when I'm looking at information coming from the machine, I need to know, for instance, if I'm looking at vibration, am I manufacturing parts that have different hardnesses? Because that might make a big difference in how much vibration I see from the machine, or my power draw, or different signals like that. And so if I can understand things like the ambient humidity, if I can understand what part I'm manufacturing, the different attributes of that part, and also be able to put all of that as feeds into the model, that will give me significantly better results than if I just look at one particular data stream coming from the machine itself. If I look at that vibration data in isolation of any of those other factors. And so being able to find that signal in the noise depends on how well I can contextualize the information. And this just goes further to show some of those different factors that you might want to utilize in order to build up the context of the information that you see. So just as an example of this that we've done with an actual customer, we connected to the machines on the shop floor and brought in information from the PLC, as well as additional sensors, looking at vibration, noise, power consumption, some of the time series information coming from the PLC itself. And we pulled that into one of our partner solutions, ThingWorks from PTC. And we connected the information to those sources. We built our domain model, our business logic, UI elements, et cetera. And we can see that in this layer here, where as the wheel was wearing down, we can see how much significantly higher the variability is in these variables than when we have a new wheel. And then we can actually see when we have a failure for that grinding wheel, what that looks like as well. And as soon as we see that failure, then we know we're making bad parts at that point. So the goal of this process was to get as much life out of the grinding wheel as possible without subjecting ourselves to the bad parts. And so we were able to create this model and be able to utilize those wheels much longer and reduce the quality. So we got savings from two parts: the longer wheel life and lower consumption of those tools, and then also we reduced our rework and scrap in the process. And then the end user was able to visualize that on a tablet from mobile alerts, and optionally we could even do that through an AR interface type thing. So if we look at some of the primary causes of variation, um, if we look at traditional fishbone diagram of what can cause a defect, we've got man, machine, method, material, measurement, environment. I don't want to go too deeply into all of these today. I'm going to do a pretty high level on man, machine, and method. Maybe I'll circle back and do material, measurement, and environment at another time. But if I look at manpower and I look at the, why manpower causes variation in the process, it could be that he doesn't know the standard work. It could be that he's not following the standard work. It could be that we've got a new worker in place. Someone may be there as a substitute and so forth. And they may not have the visibility of that, or there may be a lack of discipline in place. And so, if we look at how we can address this, there's certainly an aging workforce, and we've got a lot of turnover that's happening within manufacturing. And being able to get new workers up to speed is going to be even more important as the baby boomers are retiring and so forth. And so being able to put that expert system in place, or not expert system, but expert guidance in place, whether that's through an AR interface like this, or whether it's through other means of digital work instructions, is going to be very important for both upfront training and then as they run the process itself until they become experts in the process. And then being able to provide remote assistance where you don't have to have an engineer go to the machine. They can help remotely for things like maintenance, standard maintenance, routine maintenance, and so forth. From a machine perspective, it's certainly what we think about most of the time as being the sources of quality issues. And I've talked a lot about the predictive maintenance, and a lot of what I talked about there is specifically around the inherent variability in the manufacturing process itself, and how can we utilize that data in order to identify what are those causal factors, what are the contributing factors, and being able to mitigate those as much as possible so that we can reduce that inherent variability and identify and eliminate special causes of variation as well. Then from a method perspective, being able to document that standard work, make that available to people, and then eliminate other sources of quality issues from a method perspective. Just having the right materials in the right place at the right time, being able to have the right testing in place, the right process controls in order to make sure that we eliminate, again, some of those special causes of variation. Some closing thoughts here. From an escapes perspective, because again, quality issues getting out to our customer are the biggest cost that you can have, because it not only is a direct cost of replacing that product and so forth, but you can lose contracts with B2B customers, or reduce or undermine the confidence of consumers in your product if you're more B2C focused. So being able to eliminate those, whether it's through connected testing, so I can aggregate the testing results across the different processes, whether it's through advanced vision systems or better error proofing in the processes themselves. Those are all things that can contribute to preventing those escapes. Connecting warranty to the plant floor so that I can identify again and correlate, what are the causes from the shop floor that could end up having something in warranty downstream, and being able to utilize that information to draw those correlations and make that change. And then, some closing thoughts. IoT is really just an evolution of things that have been in place for years: SCADA systems, OEE systems, MES, et cetera. It's just a newer version of all of those things, and being able to tie that into the machine learning provides significant additions to traditional tools. And IoT has the flexibility of really getting embedded into something like a FMEA process where you can design an interface that utilizes that IoT information to have that evergreen FMEA or value stream map, et cetera. Augmented reality is more of a brand new tool for manufacturing where, not only from a work instruction side and so forth, but also from error proofing or process feedback point of view. One of the really great applications that I've seen for that is in a welding process. They give the welder real-time feedback on the quality of the weld that they're making as an overlay right on the weld as they're performing it, within the welding visor. And that is so powerful in terms of increasing the accuracy and precision of those welds, and the overall quality of the weld that you're getting. And there's opportunities to do that in pick and place operations and any number of different operations within manufacturing. So you can give the operators that real-time feedback, that real-time error proofing, and radically improve the quality of the work that they're doing. So final note, in order to be effective, the tools have to become part of standard work for multiple organizations within the company. You can't just, again, wear a Fitbit and expect to get thinner. It just doesn't work that way. You still have to do the exercise. You still have to, change your diet and so forth. And it's the same thing with, these processes on the shop floor. You can't just put an IoT device, out on the shop floor and expect that the process is going to get better. Fundamentally, people have to behave differently tomorrow than they do today. The process has to change. And so how you can actually integrate these tools into your lean processes, into your OpEx processes, and into the daily practices of your organization is really the key driver for getting the types of improvements that we're talking about. And so that's what my organization helps with and focuses on, is not only understanding the tools, but how to integrate them with those lean practices. So I want to thank you for your time this morning. And if you have questions, please reach out to me at tim@visualdecisions.com, or you can see my phone number there. The presentation will be available on my website at visualdecisions.com within a couple of days. And you can also download a copy of the presentation from there. So with that, I thank you for your time this morning. And if you have a question, please reach out to me. Thank you very much.